dropped by mistake and stuff like that. So I just like to check. Okay, we're in 7.2. And we're doing, we're still doing U.S. customary units, which means we're still using these conversion factors to go from one unit to another. The conversion factor is often very different from another problem. That's the U.S. customary system. So any questions on the homework, and then we'll go on and do the good system. Yes. 383. And this is 7.2. Okay, Gill is a distance runner. The durations of the training runs for 1 week are given in the table. Find the total time that Gill ran that week and express the answer by using mixed units. So there's this little table here. Let's just put the numbers in. You've got 7 days. And the usual. And here we have 1 hour, 10 minutes, 45 minutes. Now I'm going to put minutes above minutes. I'm going to line them up because that's actually how we're going to deal with this. We're going to have columns of hours and columns of minutes. A day of rest. It's the wrong day, but that's okay. Okay, so that's what the table says. Now they want the total distance that he ran that week, total time rather, that he ran that week, and they said to use mixed units. Okay, so in a sense, these are minutes and minutes can be combined. They're like apples and apples, that's fine. Hours and hours can be combined. They're like oranges and oranges. But mixing them takes a little more work. So we're going to have to be careful with it. Let's do the minutes first. All right, we've got 10 added to 45, we do 55, and 20, that's going to be 75, and 30, 105, and 50, 155 minutes. Over here in hours, 1, 2, 3. Okay, now the problem, of course, is that 155 minutes, because that's more than 1 hour. So in order to make this nice and neat and convey it to people in a way they can understand, what you do is take that 155 minutes and say, okay, you know that every 60 minutes is an hour, and there's two 60s in there, huh? That would give you 120. So there's 2 60s, so this has got to be 2 hours, but there's some left over, because 2 hours is 120.
25 minutes?
155, so that's going to be
25?
No,
35. 35 more minutes. Okay, that's 2 hours and 35 minutes. So you take that 2 hours, put it back over here with those, and you've got 5 hours and 35 minutes. Okay? Yes?
This is on 7.1, and it is number 81.
Which one?
81.
81.
And, yeah, but chapter 7.1.
Okay. Okay, Jessica wants to put adhesive outdoor tread on the 14 steps leading to her front door. Her plan is to center 2 strips of tread 4 inches from the edges of each step, as shown in the figure. If the tread is packaged in 5-yard rolls, how many rolls should she buy? Okay, so what we've got here, just to put the sketch up here so you can all see what she's trying to do, you've got one tread that looks like this. The other one is closer to the edge, which makes sense because that's where people tend to step on a step. Okay, this is a distance of 4 inches, and this is a distance of 4 inches, so she's centering them. And same down here for this one. this entire thing is 32 inches. Okay. So let's see how this works out. We've got 14 steps, we should put that down, huh? 14 steps. And the size of the rolls is 5 yards. Okay, so can we figure out how long this is, huh? What that distance is right there. We know that you're centered between the two edges of the step, 4 inches here, 4 inches here, and we know the whole thing is 32. So if we subtract 4 inches from 32 and another 4 inches for that side, we'll actually have this distance right here, which will be that side of the strip. So that's taking 8 inches away from 32. And that's going to be how many? 24 inches. Right. Okay. But each step has 2 of these, right? So that on one step, you're going to have 2 times 24, or 48 inches of this adhesive strip that she wants to put on. Okay, and you've got 14 steps. So we have to multiply that by 14, because in other words, this is repeated addition. So we're going to multiply it by 14. Okay, 48 times 14, and let me get that out. I haven't used my calculator in 2 weeks. She's probably given up on me. You still there? She is. Okay. I get 672 inches.
Is it 162?
Pardon?
172?
I get 672. 672. She's never been wrong, really.
Oh, okay.
I don't dare say she's wrong. She gets very upset. Okay, so now what we need to do is convert that into yards. Because the question is, this is equal to how many yards? Because we know that the actual strips come in 5-yard rolls. So let's see. All right, we want to convert inches into yards. So we create a conversion factor. Now that comes out of the table at the beginning of the section. But the way you do it is you create a conversion factor, meaning a fraction. In the denominator, you want the same unit that you've got up here so they can cancel out. And in the top, of course, you want the unit you're going to. So you want a conversion factor between yards and inches. Okay? So what do we know about that? 1 yard is...
Don't you have to do inches and the feet first before you can do it?
You can. In this case, though, that's such a common thing between yards and inches. Most people know that that's 36 inches. Now this, for example, is not a yardstick. This is a meter stick, which we'll talk about today.
Okay.
But in the old days, these are yardsticks. The difference is only about 3 inches. So this would be a yardstick up to here. Okay?
Okay.
And most people, I think, realize that that's 3 feet and each foot is 12 inches. So this is 36. So that, I would say, just use 1 there. You know, the fewer the calculations, the less chance for error. So I would say 1 yard, 36 inches. But you could go through feet if you want to. Okay, so there goes the inches. Yes?
I have a question. I was wondering if you can do 15? No.
We haven't finished this yet.
Oh, okay.
We've got a lot more to go here.
Oh, okay.
Okay. All right, so we've got this number, 672 divided by 36, and this will be in yards. And the amazing Kruskin says that's going to be 21 yards. Exactly 21 yards. Okay? But I'm not finished yet. Can you just wait till I finish the problem? Okay. All right, so that's how much she needs for her 14 steps, right? But we know that each roll has 5 yards in it. Well, 5 goes into 21 4 times, but there's a little leftover, isn't there? There's 1 yard left over. So in order to get this done, she's going to have to buy not 4 rolls, but 5 rolls. Yeah. So the answer is 5 rolls. Okay, now it's done.
The book said 4 rows.
The book said 4 rows? Are they
Yeah,
wrong
20,
again?
yeah, the book says 4.
Well, it seems to me this is all correct. I don't see any problem here. Let me multiply that again, maybe I pushed the wrong buttons. Hang on. All right, 48 times
Times
14.
14.
Yeah.
It's 672. So the book is wrong, folks, sorry. Did you get an answer?
Yeah,
Yeah.
I've got a different one, yeah.
I mean, it can be wrong. There are times when it's wrong, so that's it. Okay, Jessica,
Oh, I was just wondering if you can do 7.2, number 15.
number
15?
15
Yeah,
in 7.2?
yeah.
Even in the testing program, you know, that prints out your tests, they do make mistakes sometimes. Sometimes they give you the wrong answer, or they give you two of the same answers. So, I mean, some people who write books make mistakes, that's the way it is. Okay. We all do, don't we? Got any perfectionists in here? No? I have one in my algebra class. She is absolutely convinced that she's perfect.
That's pretty.
Uh-huh. Okay, this is 7.2, number 15. I gave up a long time ago on that. All right, it says, fill in the blanks with the correct units. It says 1 gallon is equal to 4 something. And the question is, what's the unit? They don't want the number here, they want the unit.
Mhm.
1 gallon is equal to 4 something, huh? Well, for that, you'd have to go back to the table again, and it's on page 419. Talking about capacity here, and down at the bottom, you find out 1 gallon is equal to 4 quarts. So the unit is quarts. Okay, all they want is the unit, that's it. 29? 79. We don't have that down as a problem, we did, that's okay, you can still do it. All right. This is 7.1, number 79. It says a picnic table requires 5 boards that are 6 feet long, 4 boards that are 3.3, well, I'm sorry, 3 feet, 3 inches long, and 2 boards that are 18 inches long. Find the total length of lumber required. Well, it's a matter of adding these numbers to each other, 6 feet, and then 3 feet, 3 inches, and the other one is 18 inches. Now, how many of these do you have? The 6-foot ones, you have 5 of those, huh? So 5 times 6 is going to give you 30 inches, 30 feet right there, excuse me, that's 30 feet. Okay, now the 3.3 ones, you have 2 of these. So it's 2 times 3 feet, 3 inches, which is going to be 2 times 3 feet is 6 feet, and 2 times 3 inches is 6 inches. Okay, this one, you have 2 of these. This is 18 inches. And 2 times 18 is going to be 36 inches. Yeah, exactly. All right, so this is what we want to add up. Let me just move this one over a little bit, and we'll have them all lined up nicely. This is 30 feet. Okay, so we've got inches above inches and feet above feet. And that's basically the way you handle these things. You keep the same units in the column. So 6 added to 36 would be 42 inches. And this would give you 36 feet. But again, you're running into the problem there that that's more than 1 foot. Huh? So each 12 inches is 1 foot, and there's, how many 12 inches is there? Well, there's 3 of them, that's 36. And then a little bit of leftover, huh?
6 inches.
That's going to be 3 feet, and the leftover is 6 inches. So you take the 3 feet, put it back up there, and you get 39 feet, 6 inches. And that's how much wood you need. You should buy a little more, though.
Mr. Little,
Yes.
the 3 feet, 3 inches is 4 boards.
This is 4?
Mm-hmm.
Oh, that's gonna be more than. Okay, so that's just gonna change these two numbers. 4 times 3 would give you 12, and again, 12 here. Okay, so let's go re-adding them now. This will give you 48 inches, and this will give you 42 feet. Okay, 48 inches is 4 feet, isn't it? So just simply consider that to be 4 feet, put it back up here, so you get 46 feet. But again, when you do a project like this, always get some more. You know, just a little extra you can put in the fireplace, no big deal. Just in case you make a mistake, you know how it is. All right. Are you ready for the good one now? Are you tired of all this foolishness? Conversion factors, blah. Who cares? Okay. Now, if you don't have your book, please look on, because some of the diagrams are quite good. We're back in 1790 in Paris, France, and the French Academy of Sciences decides, enough of this unit stuff. Every country has different units and the conversions between. See, one of the things is that causes the problem here is that not only do we have different units, we have different units for the same kind of thing. Here, let's think about length, okay? Well, obviously, we've got feet and inches, right? But we also have yards, we have miles, and converting between all those things, we're still in the same kind of thing. We're just in distance, right? But converting between them requires a different conversion factor for every pair you want to go between. Okay? And there's not a whole lot of sense to it at all. So that makes it very complicated. And especially when children are going to school, I mean, if you have children who are attending school now and they're learning this kind of stuff, their heads are spinning. They don't know what to do with this. This is complicated. Now let me show you what children in Europe learn. This is just amazing. First of all, rule number 1 for the metric system is there is 1 unit of length for every one of the different things. 1 unit of length for distance, 1 unit of capacity, 1 unit of weight. Very nice, huh? So, all right, that simplifies things tremendously. Now you say, well, yeah, but what if I want to go to a distance that's longer than a meter? This is a meter stick, okay? Let's suppose I want to go to a distance that's much longer than this. Suppose I want to talk about the distance between here and San Francisco. Well, you just talk about multiples of this, but the multiples will be products of 10. Everything is multiplied or divided by 10 in the metric system, which means the metric system is the decimal system for units. Now you know how easy it is to multiply a number by 10. It's a decimal number, there's nothing to it. You move the decimal point around, right? That's all you do. Same thing with the metric system. Very simple. To give you some historical background there, the little picture of the Earth there, back in the 1700s, they decided that they would determine the meter, which is their basic unit of length, by 1/10,000,000th of the distance between the North Pole and the equator going through Paris, France. There's only a problem with that, and the problem is that changes. The Earth doesn't remain the same size all the time. I mean, anyone ever been in an earthquake? Yeah, it's moving around, isn't it?
Yeah.
And as a matter of fact, the Earth does shift in other conditions too. The center of the Earth is actually liquid. So we're on a planet that is sort of, like a bubble or a balloon full of water. It has a shape for a while, but that can change, because it's liquid on the inside. And the crust is extremely thin. I mean, relative to the diameter of the Earth, the radius of the Earth, the crust is very, very thin. And that's why we have what we call an active planet. Yeah. I used to teach over at the postgraduate school. And over there, we have officers from the Navy primarily, but any of the branches of the services. And these are very well-trained people. They're the higher rank officers, from lieutenant commanders up to, captains, admirals, and stuff like that. And those are our students over there. And so one day I was teaching, we were up on the 3rd floor of one of the modern classroom buildings. we had an earthquake. It was maybe 1 or 2 in the afternoon. And it was quite a roller, you know how they are. Sometimes they roll more than others. You should have seen that class. I mean, I wish I had a video of that. That was unbelievable. Most of them weren't from California. They'd never been in an earthquake before. And here you have all these guys who are running nuclear submarines, you know. They've got the codes to launch the nuclear submarines, right? And they turned white. I mean, it was just, they thought that was it, this is the end, as pale as it could be. I said, don't worry, it happens all the time here. You know, relax, you know. If you want to, get under your desk, it doesn't matter. And after about 5 minutes, everything calmed down. They came back out from under their desk. Made me think, you know, what happens when they're under the ocean with other ships and stuff like that. All right, so that's enough of that. Okay, so the Earth changes, so that's not a good way to measure it. The modern way is right there in the middle of the page, and this will probably bore you to death. The meter is defined as the distance traveled by light in a vacuum during 299,792,458th of a second. Wow. Right? Fascinating. All right, if you went to the Bureau of Weights and Measures in Washington, you would go into a room, you couldn't go into it, but you could see it from the outside. And they would have what they call a meter bar in there. And that meter is exactly, you know, it's this distance, but held at a constant temperature and humidity, so that as far as they can make it, it's the standard meter for this world and so forth. However, that is the actual definition right there of what a meter is. Physics, for example, uses that definition. Okay. The next thing they do is show you the metric units of length, and that's at the bottom of page 425. There is a table, 7-3, and you should take a look at it, because what's going to happen here is the metric system signifies different units of length with prefixes. They all have the word meter on them, but you know, if you're talking about 1,000 meters, and they put a prefix in front of meter, and they call it a kilometer. Kilo meaning 1,000. Okay, so kilo matched up to meter gives you kilometer. And the whole prefix system is written there. Not only is the prefix system there, but it shows you the abbreviation for a kilometer. And that is km. All right? If you want 100 meters, then you can see the abbreviation is hecto, H-E-C-T-O. This is rarely used. The military uses this, but that's about it. And the military, by the way, does run on the metric system.
Is this 7-2 or 7-3?
This is 7-3, but there's no dash, it's a period actually. A decimal.
Yeah.
All right, so it's called a hectometer, that next one, and that means 100 meters. Now, why would the military use that? Because they're talking about field operations, right?
Yeah.
And they want these tanks to move forward 100 meters, okay? Well, the meter's too small for that, the kilometer's way too big, so they need something in between. So they're talking about hectometers. So that, notice, is 1/10 of 1,000, isn't it? So the difference there between the two measurements, the two prefixes, is one denotes 1,000, the next one denotes 1/10 of that, or 100. And then you're into what's called a decameter, D-E-K-A, that's 10 meters. Now you use 10 meters to talk about maybe the width of the room. Decameter would be appropriate for measuring a distance in this room. Then you have the actual unit itself called the meter. Now you start talking about things that are smaller than a meter. And the first one smaller is called a decimeter, D-E-C-I. And you can see all the abbreviations there. The one that's kind of confusing is decimeter and decameter, because, you know, that sounds too similar, and they're written in a rather similar way. But notice the prefix is different. For a decameter, it's D-A-M, and for a decimeter, it's D-M. Okay? This is the only part of the metric system that's a little bit touchy. You got to know the prefixes and their abbreviations. All right, if you want to get smaller than a decimeter, which is 1/10 of a meter, remember this is a meter. Okay? This is it right here. This is an actual meter stick. This is not a yardstick. So this is roughly 39 inches. It's a little bit bigger than a yard, the extra 3 inches out there. Okay, a decimeter would be 1/10 of this. Well, if you look at the larger numbers here, this is 10, 20, 30, 40, 50, and so forth. Each one of those divisions, like this one right here, that's a decimeter. Okay? And this is another decimeter, and so forth. And you get 10 of those in a meter. All right? Now, if you go to the next one, you go to what's called a centimeter, C-E-N-T-I, CM is the abbreviation. Those are the smaller numbers here. So in a decimeter, which is this big, you have 10 of those centimeters. So a centimeter is a little tiny thing. If you're familiar with keyboards for computers, the little keys, they're about a centimeter wide. Okay? Now, there's 10 of those in a decimeter. So how many are there in the meter? Well, if you add them all up, there's 10, 10, 10, 10, 10, 10, 10, 10. You get 100. Therefore, the abbreviation is centi. Centi always means 100. So there's 100 of these little measurements in this entire meter. But they go down further. Now, they don't give any numbers to these, but there's these tiny little measurements on top. Okay? If you take 1 centimeter, one small little centimeter there, and look at how many subdivisions it's got in it, again, you'll find 10. No big surprise, right? Those are called millimeters. So each one of these centimeters has 10 millimeters in it. How many centimeters do you have in the whole thing? 100. So 100 times 10 is 1,000 millimeters. Go with it, all the way across the meter. Huh? So the abbreviation milli, which is just simply mm, it denotes 1,000th of a meter. Centi denotes 100th of a meter, and deci denotes 1/10 of a meter. Huh? If you look at it this way, the meter is right in the middle of it. If you go down below the meter and you go up this table, then you multiply by 10 every single step, all the way up. If you start at the top of the table and you go down the table, you divide by 10 every single step of the way, all the way down. So to convert between any two sizes of measurement, between a millimeter and a centimeter, or all you do is multiply or divide by powers of 10. That's it. So no weird conversion factors like the U.S. customary system. It's very simple. And it's actually even simpler than it sounds. If you go on to page 426, you actually have a part of a meter stick there. And that is to scale, by the way. You could actually use this to measure things. And you can see that they do put inches on the bottom there to give you some feeling for the connection between the metric system and the U.S. customary. But you've got there, basically you've got a decameter there, huh? A decimeter, I'm sorry. And you see the centimeter marks, and in between you've got these little tiny ones, those are the millimeter marks. Okay. Then they give you some feel for what all this is about. They put a penny on that scale and ask you what is the width, the diameter of the penny. Well, it doesn't go quite to 2 centimeters. It's a little bit less. It's 1.8, and you simply look at that, the little divisions there. There's 1 centimeter, and then there's 8 of those little divisions, which is 1.8 of centimeters for the width of the penny.
How do you get there? How do you get the circumference of the circle?
How do you get the circumference or
The
the
perimeter.
circumference? Yeah, the perimeter of a circle is called circumference, but that's a complicated formula. That formula looks like this. The circumference is going to be 2 pi r. So in order to figure out what this is, you have to have the actual diameter, and that's what this is. That they're showing you the diameter. It turns out that this, from here to here, is 1.8 centimeters.
Times itself again?
Hmm?
You times itself again to get the...
That's right. What you do is multiply all of it up. So it would look like this: 2 times pi. Pi almost always is 3.14. It's an irrational, so you use 3.14. And then you put in this 1.8. And multiplying that out, you get the circumference all the way around. So you have to actually do a calculation for that. So it's 2 times 3.14 times 1.8. This turns out to be 11.30. Now, remember, we're working with centimeters here, huh? Okay. So, as far as we're concerned, what we're really interested in here is working with the metric system in the same way we just finished with the US customary system. And that is, we want to convert between units. Extremely easy to do. Now we're going to start off by doing it the hard way, and the hard way is simply using conversion factors. And that's not hard, we just finished doing that with the US customary system, but you can't do that if you really don't know what you're doing. It's possible to do it that way. And then we'll look at the easy way. For example, let's suppose we take 10.4 kilometers, and that's equal to how many meters? Okay. Well, all we have to do is put in a conversion factor between kilometers and meters, and cancel out units as we usually do. So 10.4 kilometers wants to be multiplied by a conversion factor. You want kilometers down here, and you want meters up here. Huh? So you find out, by looking at that table there, that 1 kilometer is 1,000 meters. Okay? Cancel out the units just like you do in the US customary system, and you're left with meters. And you have to multiply the 10.4 by 1,000.
So
Well,
10,000.
multiplying by 1,000 does wonderful things to decimal measurements, right? Very easy. You just shift that decimal point. Every time you multiply by 10, you're going to shift the decimal point 1 to the right. The number gets bigger. And you're multiplying by 10 3 times, right? So it gets shifted over 3 times. So it becomes like this. Boing, boing, boing. So you have 10,400 meters. So simple. Now that's doing it with the conversion factor idea. And you can always do that. You're welcome to. But here's how the kids in Europe are taught. It's much, much easier. What they do is they take this table that you have on page 425, the one down at the bottom of the page, the metric units of length and their equivalents. Okay, they take that and make it a horizontal table. And they do it in the following way. They call it the prefix line. And it looks like this. In the center of the prefix line, you have your basic unit. In this case, we're talking about distance, so it's going to be meter. Over here, you have the decimeter. Then you have the centimeter. Then you have the millimeter. Over here, they put the larger amounts, the larger sizes. So this is the decameter, that's 10 meters. Then you have the hectometer, which is 100 meters. And then you have the kilometer, which is 1,000 meters. Going from right to left, you multiply by 10 to go between any two. Going from left to right, you divide by 10 to go between any two. Okay? Now, you say, well, how do I remember that? We give them a memorization technique. And here's the memorization technique. Kids have donuts until Dad calls Mom. Okay? First letters tell them how to do the prefix line. That until stands for the basic unit. Okay? Kids have donuts until Dad calls Mom. So they get their prefix line down there. Okay? And here's how they'll do that conversion. They'll say, okay, 10.4 kilometers, I want to know how many meters that is. Well, where am I starting? Now, did everyone hear that? Where am I starting? I'm starting with kilometers, which means I'm starting over here. Where am I ending? I'm ending with meters, which is over here. What do? I go to the right, boing, 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 like that, 3 times, okay? Going to the right 3 times basically means I take the decimal point in that number and go to the right 3 times. I mean, could this be easier? No, I don't see how. And they write it down just like that. Figure out which way you're going and how many, and then move the decimal point the same way. That's it. That's how you convert between different units of length in the metric system. I mean, this is very different, don't you think? Why are we resisting this? For 300 years we've resisted this. Now, in all fairness, not only does the military in this country use the metric system, but so does science, research, many areas, even medical research does. So the only people who don't do it are people like you and me. Oh, we don't want metric measurements on our speedometer. Remember there was a time, I don't know, 20 or 30 years ago, when on a speedometer they had miles per hour and they also had kilometers per hour? Yeah. And everyone said, take that off. Bit over the top, don't you think? All right, let's do some of these. Suppose we have something like this. Suppose we have 4,700 centimeters, and we want to know how many kilometers is that. All right? You can do conversion factors if you want to, but it's so much easier. Where are you starting? You're starting with centimeters. Centimeters is right here, right? And you want to go to kilometers. So how do you do that? You jump hopscotch. 1, 2, 3, 4, 5 to the left. All right, so you take this number, 4,700, there's its decimal point, it's just to the right of that far right 0, and go 5 to the left. 1, 2, 3, 4, 5. Put in that leading 0, and you have that. 0.04700 kilometers. So the prefix line determines which way to go and how far. And that's it. And you move the decimal point in the same direction, that much. That's how you convert things. I know you're in shock. This is just too easy. There's got to be a trick here, right? No, there's no trick. That's it. All right, let's look at a couple more problems here. There's some applied problems here. Down on 428 at the bottom, Mount Everest, the highest mountain in the world, is 8,850 meters. How many kilometers is this? All right, 8,850 meters is how many kilometers? Again, put the starting point and the ending point up there and just start counting hopscotch. That's it. Okay, we're starting at meters, which means we're here in the center, and we want to go to kilometers. Well, that's pretty much what we did before in the other problem. All right, it's 3 to the left. So we take the decimal point that's sitting right there right now and go 3 to the left, 1, 2, 3, and then we get rid of the question mark and write 8.85 kilometers. That's the height of Mount Everest. On page 429, a rectangular field is 800 meters by 300 meters. If a farmer has 2 kilometers of fencing, will this be enough to go around the field? Okay, so I've got a little picture there of this field, sort of on edge. This is 800, or at an angle rather. This is 300. All right, fencing would be the distance around the edges, huh? It's perimeter. Okay. So of course, opposite sides are equal in length. This is 300 meters, and this is 800 meters. So you add them all up. So you have 800 meters, 800 meters, 300 meters, and 300 meters. Add that whole thing up. It's very easy to do, 16, 19, and 22. That's how many meters? 2,200 meters. Now, they tell you that the farmer has 2 kilometers. And the question is that enough? Well, let's convert this to kilometers to see. We want to know how many kilometers is that. So we're going again from meters to kilometers, which means we go 3 to the left. That would be 2.2 kilometers. He only has 2 kilometers of fencing. The answer is no, he does not have enough. That's it. So if you remember the prefix line, and what I mean by that, that translates, that's teacher talk for memorize it for Friday. Okay? If you remember the prefix line, calculations in the metric system are nothing. They're just amazing. And tomorrow, we'll go into the other kinds of measurements. We'll go into time and mass and stuff like that. Just a short description here. In our US customary system, we talk about weight, units of weight, huh? Person weighs 150 pounds, something like that. In the metric system, they don't talk about weight, they talk about mass. Now, what's the difference? Mass is a property of all objects that has nothing to do with what planet you're on. Excuse me. Gee.
Oh, yeah, that's right.
This object has mass. Now, it also has weight, but it's got mass. If we took this up to the moon, this would weigh about 1/6 of what it weighs here. Okay, so we do. That's nice, isn't it? We weigh 1/6, I mean, you could float off. All right, but the mass of the object does not change between here and the moon. So it's got a property which is independent of what planet you're on. Okay, and the metric system looks at mass. The unit of mass is called the gram. It's a very small unit, and we'll get into that tomorrow. But let's look at some problems for tonight.
Does it have to do with the gravity though? Is mass like gravity?
No. No, weight has gravity. If you take a person that weighs 100 pounds here on Earth, okay, and put them on the moon, they'll weigh about something like 18 pounds up there. Okay? Has their mass changed? No, of course it doesn't. But their weight has changed because the pull of gravity on them is different depending on the planet. Obviously, the Earth has a much greater pull than the moon does because it's a much bigger object. So the force of gravity here is more than it is on the moon.
So if someone went to the moon and then they came back, would their mass be different or would it be the same?
The mass would be the same. The mass is the same everywhere in the universe, but the weight changes depending on where you are. Okay?
So they're gonna, the metric system uses a gram.
It uses the gram as the basic unit.
How do you measure a gram then? I mean, how do they do it? I mean, I've seen scales and they weigh the object in grams. They don't weigh the, I mean, how do you,
The modern scales convert automatically. They're digital.
uh-huh,
So they know what a gram weighs on Earth.
Right.
Okay? So they're able to convert back to grams if you need them.
but it will measure, the
But they-
mass?
No, the scale here measures weight.
Okay,
But it converts it to grams if you want to see grams. Because then they know how to convert it. The conversion factor is available. We'll get that not tomorrow, but the next day.
next, okay.
Yep.
Okay.
Okay, here's the homework problems. We're in 7.3.